A galaxy the mass of 100 billion stars was sitting in place just 290 million years after the Big Bang. Every model said that was impossible. The telescope looked anyway, and it found hundreds more. We built the most expensive scientific instrument in history to confirm what we already knew. What came back was a crisis. Mature galaxies in the universe's infancy. Mysterious objects called little red dots that fit no known category. Black holes that violated every physical limit on their own growth. And a universe whose expansion has now split cosmology in two. If you enjoy the journey, subscribe and like this one. We are going somewhere that changes the picture entirely. Stay close. We begin now. $10 billion. 20 years in the making. Thousands of engineers, scientists, and technicians spread across 14 countries. By any measure, the James Webb Space Telescope was the most ambitious scientific instrument humanity had ever attempted to build. And the scientists who built it were not afraid. They were excited. The telescope was designed to do something specific, something the field had been waiting for since Edwin Hubble first measured the distance to a galaxy a century ago. It was going to look back to the very edge of time, to the universe's first few 100 million years, and confirm the picture cosmologists had spent 4 decades assembling. The standard model of cosmology had been tested from every angle, refined by the Hubble Space Telescope, reinforced by the Planck satellite's exquisite map of ancient light. It predicted, in beautiful detail, how the universe had grown from a hot, dense flash of energy into the vast web of galaxies visible today. The model was called Lambda CDM, and cosmologists were deeply confident in it. Webb was going to show them the final frames of a film they believed they already knew by heart. The launch took place on Christmas Day of 2021 from a launch pad in French Guiana on a rocket borrowed from Europe, 18 months later than originally planned, after nearly 2 decades of engineering delays, cost overruns, and one infamous near incident during testing that almost tore the telescope apart. The spacecraft folded itself like origami to fit inside the rocket, then spent a month unfolding in space, mirror by mirror, sunshield layer by layer, each step watched by thousands of engineers holding their breath in control rooms around the world. A single stuck bolt would have ended the mission. Everything worked. The mirror locked into place. The instruments cooled to within a few degrees of absolute zero. The telescope settled into position 1,000,000 miles from Earth, at a gravitational sweet spot, where the forces of our planet and the star it orbits perfectly cancel each other out. From there, it would stare into the deep past with a clarity that made every previous telescope look like squinting through fogged glass. Scientists across the world began writing their observation proposals immediately. The competition for time on Webb was extraordinary. Roughly 10 times as many proposals submitted as the telescope could ever fulfill. Astronomers spent months crafting arguments for why their target, their question, their particular patch of sky deserved a few precious hours of the most powerful eye ever pointed at the cosmos. Most of them assumed the telescope would answer their questions, confirm their models, fill in the gaps. What almost none of them predicted was that the telescope's very first sweeps of the deep sky would generate a question for which the standard model had no ready answer, and that the question would grow louder every time a new dataset came in. By the end of Webb's first year of observations, something was already wrong with the story. The astronomers who noticed it first did not go public immediately. They sat with the data, checked it, rechecked it, and then began, quietly, to worry. The first public images arrived in July of 2022, and they were astonishing in ways that had nothing to do with what was wrong with them. President Biden unveiled the first deep field image at a White House briefing. In a region of sky so small, you could cover it with a grain of sand held at arm's length. The telescope had captured thousands of galaxies, each one a separate island of hundreds of billions of stars, their light bent and stretched by the gravity of a massive cluster in the foreground. It was the deepest infrared image of the universe ever taken. People cried looking at it. The other images followed over the next day. Dying stars. Their remnants expanded into glowing nebulae shaped like hourglasses and butterflies. Two galaxies caught mid-collision, their arms tangling. The atmosphere of a distant world passed, for the first time with real precision, into its chemical ingredients. The images were breathtaking, and the world responded accordingly. Astronomers, meanwhile, were looking at something else. Inside the deep field data, in the faint, reddest objects near the edge of detection, the early universe researchers began noticing a pattern. Lambda CDM predicted what the universe's earliest galaxies should look like at extreme distances. Faint, small, irregular blobs of star-forming gas. The cosmic seeds that would, over billions of years, grow and merge into the grand structures visible around us today. There should have been a steady thinning out of bright objects as you looked further back. The universe, the model said, was less organized the earlier you peered into it. The data said otherwise. Bright, well-formed galaxies did not thin out the way the model required. Some of them, at distances placing them in the universe's very first few 100 million years, were bigger and more luminous than anything the model had room for at that moment in time. The initial response from several teams was that something had gone wrong during calibration. When you build a new instrument, systematic errors are common. A filter response that does not quite match the lab measurement. A detector with unexpected sensitivity at certain wavelengths. Calibration artifacts can make objects appear brighter or more distant than they actually are. So the teams checked the calibrations, carefully, repeatedly, multiple groups working independently. The calibrations were fine, the objects were real, and they were where the data said they were. While research teams were cautious in early conversations, exchanging results through academic channels in careful whispers, a phrase started appearing in emails between some of the most respected early universe astronomers in the field. The phrase was, "This should not be here." It was the first note of a song Webb would go on to play louder and louder as the months passed. Understanding exactly why it set off alarms requires one concept, a single tool that astronomers use to read the universe's past. Without it, the discoveries ahead make no sense. With it, everything that comes next lands with its full weight. Imagine every object in the universe is sending you a letter, and the letter is written in light. That light leaves the source and travels through space toward you at the fastest speed anything in the universe can travel. But space itself is not standing still. The universe is expanding, and as light travels through that expanding space, the space around it stretches. The light stretches with it. The wavelength of light, the thing that determines its color, changes when it stretches. Shorter wavelengths are blue, longer wavelengths are red. Light from a distant, fast receding galaxy arrives, shifted toward the red end of the spectrum. The further the galaxy, the faster it is moving away as the universe expands, and the more its light has been stretched on the journey. Astronomers call this redshift, and they represent it with the letter Z. A redshift of 0 means the object is essentially next door. A redshift of 1 means the light took roughly 7.5 billion years to arrive from a time when the universe was roughly half its current age. A redshift of 10 means the light left when the universe was only about 460 million years old, barely 3% of its current age. Redshift is a timestamp. Every galaxy carries one in the color of its photons. Point your telescope at a smudge of ancient light. Spread its spectrum across a detector. Find the characteristic fingerprints of specific atoms shifted off their expected wavelengths. Measure that shift, and you know exactly when in cosmic history that galaxy was alive and radiating. Here is the part that matters for everything ahead. The universe had a beginning approximately 13.8 billion years ago. For the first few 100 million years after that beginning, there were no galaxies, no stars, no light at all. There was only hydrogen and helium and darkness, a period astronomers call the cosmic dark ages. The first stars ignited somewhere around 100 to 200 million years in, burning their fuel furiously, and the first tiny proto-galaxies began to coalesce from swirling clouds of gas shortly after. So, when you find a galaxy with a redshift, placing it at 290 million years after the Big Bang, you are finding something that was already massive and already glowing with the light of billions of stars at a moment when the cosmic clock had barely started. That light has been traveling for more than 13.5 billion years to reach the detector. When it left, the dinosaurs had not yet evolved on Earth. Neither had Earth. Neither had our entire solar system. Neither had our galaxy in anything like its current form. That is what redshift tells you. That is why the Webb findings stopped researchers cold. And the galaxy that finally forced the conversation into the open was old in a way that required something to have happened before it, something that should have been, according to every model in existence, completely impossible. For most of the 20th century, the question of how galaxies form had a single, elegant answer. The universe began with density fluctuations so tiny they were quantum mechanical in origin, microscopic wrinkles in the early hot plasma. Gravity took those wrinkles and amplified them across billions of years. Regions slightly denser than their surroundings pulled in more material, collapsed into filaments, and built up structures called dark matter halos. Inside those halos, ordinary gas cooled and condensed, forming the first stars and eventually the first galaxies. Those small proto-galaxies merged with neighboring ones, combining mass and triggering new waves of star formation. Over billions of years, the small clumps grew into larger ones, and the larger ones grew into the grand spirals and ellipticals that fill the sky today. This framework is called hierarchical structure formation, and it sits at the foundation of Lambda CDM. A beautiful picture. It starts with almost nothing, and through gravity and time assembles it into everything. And it is supported by an enormous amount of observational evidence from the nearby universe. The large-scale structure of the present-day cosmos, the web of filaments and voids and galaxy clusters, matches what simulations predict. Surveys of millions of galaxies confirm the model's broad architecture. The blueprint had one specific prediction for the early universe, and it was precise. In the universe's first billion years, galaxies should be small, still assembling. The biggest structures form last, because they require the most merging events, the most time, the most raw material. A galaxy with the mass of 100 billion stars requires hundreds of smaller predecessors to have fallen together and shared their material. That process takes time. In the first few 100 million years, the model expects to find only scattered, irregular, faint collections of young stars, nothing more dramatic than the raw ingredients of the universe's future architecture. Think of it like building a city. A fully developed metropolis cannot exist on the day the first foundation stone is laid. Roads, buildings, infrastructure, networks, all of it requires decades of construction. The bigger the city, the more time the construction demands. The early universe, in this model, was a construction site with freshly poured foundations. When teams pointed Webb at redshifts above 10, they expected to find a construction site. What they found looked more like a skyline, large, luminous, extended galaxies, some of them already containing billions of stars, already producing oxygen and heavy metals, sitting in the universe's first few 100 million years, as if the construction timeline had been compressed by an impossible factor. The gap between prediction and observation was not small. The galaxies being confirmed were so far outside any reasonable version of the model that multiple teams who found them in the data initially refused to trust the result. And that gap, once confirmed beyond any doubt, forced a question the field had never truly had to ask before. What if the blueprint was wrong from the start? The region of sky, chosen for Webb's first deep look, had been selected precisely because it appeared to contain nothing, no known clusters, no bright stars nearby to contaminate the data. a patch astronomers had previously examined with older telescopes and seen only the faintest whispers of distant objects. It was chosen as a clean window, a region of pure darkness. If you want to see the faint light from the universe's first billion years, you start by looking somewhere where nothing gets in the way. The survey team spent months planning this observation. They pointed the telescope at that blank region and collected light for hundreds of hours. The result was an image so deep it captured objects at distances the previous generation of telescopes could only theorize about. Then the data processing began. The faint red objects at the edge of detection, the ones sitting at the highest redshifts, and therefore the earliest moments of cosmic time, were supposed to be sparse. The model gave specific predictions. At extreme distances corresponding to the universe's first 400 to 500 million years, a survey field should yield a modest count of faint irregulars, small scattered knots of early star formation. The team was prepared to announce a handful of candidates and call it a successful pilot program. The object count came back significantly higher, and the objects were brighter than predicted. Significantly brighter, by a margin that went beyond any plausible calibration error. The team spent weeks checking their analysis pipeline. New measurements, new reductions, different researchers running the analysis independently to confirm there was no software artifact creating a false signal. Every check produced the same result. One object in particular stopped the analysis cold. Sitting at a distance, placing it deep in the universe's first 500 million years, it was a luminous, extended source with a brightness profile suggesting a genuine stellar population across a real physical extent, not a single bright point easily explained away as a compact, active nucleus. The team circulated the data internally, asking colleagues to find the flaw. The flaw did not appear. When they followed up with additional instruments, the object held firm, and while that confirmation was being assembled, other teams running parallel surveys with different fields and different instruments found their own anomalies. A handful here, a cluster of unexpected bright objects there, each one requiring its own explanation, each one resisting every obvious systematic. The follow-up requests began piling up. More telescope time, spectroscopic confirmation, verification from radio observatories capable of detecting the specific emission lines of oxygen and carbon from objects at extreme distances. What came back over the following months was not one confirmed impossible galaxy, it was hundreds. Among the hundreds of early galaxy candidates pouring out of Webb's surveys, one stood apart from the moment its distance was confirmed. The Deep Extragalactic Survey team found it in their fields. A point of light at extreme distance that kept surviving every test designed to rule it out. To confirm its redshift spectroscopically, they enlisted the Atacama Large Millimeter Array, a collection of 66 radio telescope dishes arrayed across a high Chilean desert, capable of detecting the specific emission signature of ionized oxygen from galaxies at the farthest reaches of the observable universe. The signal came back at a redshift of 14.18. Run that number through the cosmic clock. A redshift of 14.18 places this galaxy at just 290 million years after the Big Bang. To appreciate what that means, consider that the entire age of the universe stretches across nearly 14 billion years. 290 million years after the beginning is less than 2% of that total. On a scale where all of cosmic history fits in a single day, this galaxy existed at roughly 25 minutes past midnight. The object carries a catalog designation, JADE-SGSZ140. Technical and unmemorable. What it describes is neither. The galaxy is large. The light coming from it is not the pinprick of a single bright source, which could be explained away as a lone active nucleus. Measurements of its physical extent show the light comes from across a genuinely wide, populated galaxy. Its ultraviolet brightness makes it one of the most luminous objects found at such extreme distances. Something containing billions of stars was shining at a distance of more than 13.5 billion light-years, at a moment in time when the entire universe was barely getting started. But the brightness alone was not what alarmed the field. Inside the spectroscopic data, the team found oxygen. Oxygen does not exist naturally in the universe from its formation. There is no primordial oxygen, no oxygen left over from the Big Bang. Every atom of it has to be manufactured inside a star, forged in nuclear reactions that occur in a stellar core when it fuses lighter elements together. When that star exhausts its fuel and explodes as a supernova, it scatters those heavy elements into the surrounding gas. The next generation of stars forms from that enriched material, and the generation after that inherits it further. Finding oxygen in a galaxy 290 million years after the Big Bang means at least one full generation of stars had already been born, had lived out their entire lives, and had died in explosions violent enough to scatter their contents across space. All of that had already happened before this galaxy even qualifies as early. The galaxy confirmed in that Chilean desert data is a second-generation galaxy at minimum, and the first generation, the one that built the oxygen this object carries, has already vanished completely. Oxygen is the third most abundant element in the universe, found in your lungs, in the water, in your glass, in the rocks beneath your feet. But every atom of it was once inside a star, every single one. The oxygen you breathe right now was forged inside a stellar furnace that burned out long before our own star ignited. Scatly. A star massive enough to produce significant oxygen will exhaust its fuel in only a few million years before exploding and scattering its newly minted elements into the interstellar medium. So when scientists found oxygen inside a Procer galaxy at 290 million years after the Big Bang, they had to trace the logic backward. For oxygen to be present in that galaxy, at least one previous generation of massive stars had already completed its entire life cycle. Those stars had to have formed, perhaps in the very first 100 million years after the Big Bang. They had to have burned through their fuel over the next few million years. They had to have exploded and released their products before the galaxy confirmed by the radio array even assembled itself. A complete stellar generation, from birth to death, fitting inside a window of perhaps 100 million years. This is what astronomers mean when they say the universe was running faster than predicted. The first stars had to ignite earlier than models suggested, burn hotter and faster than expected, die more violently and efficiently than any calibrated simulation was producing. The galaxy found at 290 million years is, in a very real sense, already ancient. A second or third chapter of the universe's story, written before the field had even finished reading the first page. Here is what makes this particularly unsettling. The first generation, the one that produced all that oxygen, the stars that actually lit the cosmic darkness for the very first time, is already gone by the time Webb looks at this object. The telescope is watching the grandchildren of the universe's first light. The grandparents had already vanished before a single instrument ever turned toward them. Every model of how the first stars formed had placed their ignition later than this implied. Simulations of the cosmic dark ages, the long period before any light existed, had predicted gradual star formation beginning well after the first 100 million years. The oxygen in this object says that timeline was wrong, potentially by a large margin. And even as the field was trying to absorb that possibility, a separate survey team was finishing its own analysis of a different object from Webb's data. The record had been set, but records, in this story, were built to fall. Science rarely stands still long enough for anyone to celebrate. The confirmation of the 290 million year galaxy was published and announced in the spring of 2024. The team had done everything correctly: multiple telescopes, spectroscopic confirmation, radio telescope verification. The redshift was locked in with 6 sigma confidence, meaning the probability it was a statistical fluke was smaller than 1 in half a billion. For a brief moment, It stood as the most distant confirmed galaxy in human history. That record lasted less than a year. A survey team was working through a collection of Webb data under a program named, fittingly, Mirage or Miracle. The name captured exactly the uncertainty hanging over every extreme early universe detection. Was the telescope genuinely seeing the impossible, or was some unidentified artifact mimicking a distant galaxy? The program was designed specifically to chase the most extreme candidates and find out which category they fell into. One candidate in particular had caught the team's attention. The preliminary estimate of its distance was extraordinary, pushing even beyond the previous record holder. When spectroscopic confirmation arrived using Webb's near-infrared spectrograph, the result came back in early 2025 with a redshift of 14.44, plus or minus 200ths. This galaxy, now called MOME Z14, sits at 280 million years after the Big Bang, 10 million years earlier in cosmic time than the previous record holder. Multiple distinct ultraviolet emission lines appear in its spectrum, making the redshift measurement unusually robust. Confirming a high redshift galaxy with a single spectral feature leaves some room for debate. MOME Z14 had several independent features, all pointing to the same number. The record had fallen. The significance of this object goes beyond the simple fact of its distance. Its existence pushed the pattern one more step in the direction that was troubling theorists. Two confirmed massive, luminous galaxies sitting in the universe's first 300 million years, within 10 million years of each other in cosmic time. Meanwhile, photometric survey candidates were piling up at even higher redshifts, with preliminary estimates placing some of them before 200 million years after the Big Bang. The field now faced a question the standard model had never been asked to answer. If confirmed galaxies are appearing at 280 to 290 million years, and photometric candidates hint at objects even earlier, where does the population actually cut off? The cosmic dark ages were supposed to end gradually, with the first stars igniting sporadically and unevenly. The universe appeared to have flipped a switch instead, assembling large, chemically enriched galaxies with a speed the timeline had no room for. What made it worse was not the individual records. It was what happened when teams looked in every direction and counted what they found. Finding one impossible galaxy can be explained away. Cosmic variance is real. The universe has patches where matter happened to concentrate slightly earlier than average. A single outlier sits comfortably within the margin of statistical variation. Finding hundreds of them from every survey team in every direction the telescope points is a different kind of problem entirely. The number density crisis began to take shape through one specific measurement. When the Deep Survey team calculated how many bright, massive galaxies they had found per unit of sky in the universe's first few 100 million years, and then compared that number to what lambda CDM simulations predicted for the same slice of time and space, the ratio was staggering. The observed number exceeded the predicted number by a factor of more than 100. Let that settle. The model predicted, say, one object per survey volume. The telescope found more than 100. Calibration issues might bump a measurement by 10 or 20%. Systematic biases in redshift estimation might shift some objects from one cosmic epoch to a nearby one. A factor of 100 replicated across independent teams using different telescopes, different analysis pipelines, and different fields of sky is beyond any plausible instrumental explanation. The teams that published these results were careful in their language. Phrases like significant tension with theoretical predictions and potentially challenging to standard hierarchical assembly appeared where less restrained researchers might have written something far blunter. Science is a careful discipline. Extraordinary claims require measured presentation. Privately, the conversations at conferences took on a different tone. Researchers who had spent careers building and refining the standard model of galaxy formation were asking the same question in hallway exchanges and over coffee. What if we simply got the early universe wrong? What if the model that correctly predicts everything about the cosmos from roughly the first billion years onward has a fundamental error somewhere in its description of the first few 100 million? Two interpretations sat at the center of every debate. Either the observations were wrong in some systematic way no one had yet identified, an error hiding in the data that would eventually surface and resolve the discrepancy, or the observations were correct, and something fundamental about how early cosmic structure forms was operating differently than every model predicted. Each option carried enormous implications. Finding a hidden systematic error would be embarrassing but manageable. Discovering that lambda CDM genuinely fails in the early universe would require rethinking physics the field had treated as settled for decades. And just as that debate was heating up, Webb delivered something that forced a different kind of question entirely. Inside the universe's first 2 billion years, the telescope found a galaxy that should have been structurally impossible to build that fast. A galaxy with a shape that required more time to assemble than the universe had yet provided. Spiral galaxies are the universe's precision instruments. Building their elegant, ordered arms requires two things the early universe violently resisted, providing time and stability. Spiral arms are the result of gravitational density waves, propagating through a rotating disk of stars and gas over hundreds of millions to billions of years, slowly organizing chaos into geometry. That process is also delicate, easily disrupted by the gravitational violence of a close encounter with another galaxy. In the early universe, both time and stability were in short supply. Galaxies were forming, colliding, and merging at a rate far higher than today. The universe was smaller then, more crowded. Galaxies were constantly crashing into their neighbors. Every major merger disrupted disk structure, converted ordered rotation into chaotic tumbling, and produced the puffed-up, disordered elliptical galaxies that dominate today's older galaxy populations. The early universe was a demolition derby. Spiral arms, under those conditions, should have been nearly impossible to maintain. So, when Webb's images in early 2025 revealed a galaxy with clear, well-developed spiral structure sitting within the first 2 billion years of cosmic history, arms intact and measurably rotating, the reaction from researchers carried real weight. The galaxy's spiral arms were clearly present in the data. Its rotational motion was confirmed spectroscopically. Its stellar mass was enormous. Under normal formation scenarios, a galaxy this large and this structured, sitting this early, should have been smashed apart by merger events before its arms ever had time to form properly. The fact that it had survived intact was a direct challenge to the assumption that spiral structure required the quiet, settled conditions of a more mature universe. Dr. Themia Nanayakara of Swinburne University, part of the team that analyzed this galaxy, put it plainly. The fact that this galaxy did not become an elliptical means there might be ways galaxies can grow that have never been observed before in the local universe. That phrase is worth sitting with. Galaxy growth mechanisms are not obscure footnotes in astrophysics. They sit at the center of the entire project of understanding how structure forms in the cosmos. Suggesting that unknown growth mechanisms exist means the field is missing something fundamental at a basic level, something operating in the early universe that no simulation has yet captured. The galaxy planted a seed in the field's thinking. The universe appeared to be building complex structures with a speed and efficiency that the models did not predict and current physics does not fully account for. Gravity and dark matter and gas dynamics were doing something in the universe's first chapters that our simulations were consistently getting wrong. And then, scattered across every deep field image Webb had ever taken, researchers started noticing something else. Hundreds of tiny, intensely red points of light hiding in plain sight. Objects that fit no existing classification. Objects that were, somehow, Even more confusing than the impossible galaxies, they showed up everywhere once people knew to look for them. Tiny, intensely red, almost point-like sources of light scattered across Webb's deep field images, concentrated in the period from roughly 400 million to 1 billion years after the Big Bang, dozens in each survey field, and then hundreds as more data accumulated. They were faint enough that no previous telescope had ever resolved them clearly, small enough to have been washed out or overlooked in earlier surveys. Webb, with its massive mirror and extraordinary infrared sensitivity, was the first instrument capable of seeing them distinctly enough to recognize that something unusual was happening. Every major class of object in the sky has a known spectral signature, a recognizable fingerprint of color, brightness, and emission that allows astronomers to categorize it at a glance. Stars have signatures. Galaxies have signatures broken into subcategories. Star-forming galaxies, passive galaxies, starburst galaxies, galaxies with active nuclei at their centers. Quasars have signatures. Even the exotic objects, brown dwarfs and neutron stars, and active galactic nuclei of various types have been catalogued and classified. The taxonomy of the sky is extensive, refined over decades of observation. The little red dots fit none of it. Their color was wrong for normal galaxies. Their compactness was wrong for extended star-forming regions. Their brightness profile was wrong for quasars. Some of them showed spectra with strong gas emission, but the intensity and shape of those spectral features pointed to conditions more extreme than any known nearby analog. They appeared intensely in the universe's first billion years, and then, with equal mystery, their numbers dropped sharply. By the universe's second billion years, they had largely vanished from the data, a class of objects that appeared, flourished for a cosmic moment, and then disappeared, leaving nothing comparable in the modern universe. No existing catalogue entry, no similar object ever detected before Webb. 100 questions. And the most pressing one arrived almost immediately after the first confirmed detections. Because when teams looked at the little red dots and studied the environments where they clustered, a pattern emerged that carried its own disturbing implication. These objects were not rare accidents. They were common. Perhaps the most common category of bright object in the early universe that had simply been invisible to every telescope that came before. The discovery of little red dots was, in a practical sense, the second major crisis in Webb's short scientific life, arriving alongside the impossible early galaxies rather than after them. Both problems confirmed across multiple surveys, both pointing in the same uncomfortable direction. The universe in its first billion years was doing things the field had neither predicted nor observed before, and the tools developed to understand the modern cosmos were not fully adequate to explain what Webb was revealing about its earliest chapters. Identifying a new class of object is only the beginning of the problem. Knowing these things exist tells you nothing about what they actually are, and when teams finally broke the light from the little red dots into its component wavelengths, what they found was a spectral shape that no one could immediately explain. The light from a little red dot, once spread across a detector with sufficient precision, forms a picture that no one had seen before in any astronomy catalogue. Imagine a mountain range seen in silhouette. On the left side of the peak, the light rises steeply in ultraviolet wavelengths, giving the object a blue-hot glow on that end of the spectrum. On the right side, the light drops sharply into the optical and near-infrared, giving the object a deep red color. The two slopes meet at a point, and that point forms a sharp bend, a V, right where the two very different contributions to the light converge. That V shape is not a minor curiosity. It is a clue about physics, and it rules things out the moment you look at it. A normal star-forming galaxy produces light across a broad swath of wavelengths, its spectrum a relatively smooth curve dominated by the combined output of billions of stars with a range of temperatures. An ordinary quasar, a galaxy with a violently active black hole at its center, produces light dominated by that central engine, bright with specific emission features, but shaped in a characteristic way that has been studied and catalogued in tens of thousands of objects. Active galactic nuclei of various types have their own recognizable signatures. Astronomers have developed classification systems for every known category of bright object in the universe, and within each category, the spectral shapes are reasonably predictable. A V-shaped spectrum, blue on one side, red on the other, bending sharply at the crossover point, fits none of those categories. When researchers ran it against the standard taxonomies, the match scores came back empty. Whatever was producing this shape was combining two very different physical processes in a way that the existing classification system had never been asked to accommodate. Here is what makes the V-shape most useful as a clue. The blue ultraviolet side of the spectrum is consistent with hot, young, massive stars. The kind of stars that burn at extreme temperatures, emit furiously in the ultraviolet, and live very short lives. If you wanted to produce that left side of the V on its own, you would point to a region of intense star formation, exactly what you might expect in the early universe, when gas was abundant and gravitational collapse was happening rapidly. But the red optical side, the right side of the V, tells a completely different story. That component matches the kind of glow you get from extremely dense, hot, optically thick gas that has been heated to extraordinary temperatures from the inside, radiating with a redness that speaks of conditions far more extreme than any star-forming cloud. The two signals suggest different physical origins, as if two separate phenomena are contributing to a single compact source simultaneously. That dual nature is the fingerprint that pointed in three different directions at once. Some researchers looked at the hot, dense gas and thought immediately of a black hole, consuming surrounding material at a furious rate. Others looked at the extreme ultraviolet component and thought of something even more exotic, something at the theoretical edge of what physics says a star can be. A third group proposed that the V-shape was an artifact of a specific geometry, perhaps dense gas covering most of the source but leaking ultraviolet light through gaps. The debate that followed was not polite. Papers appeared on public servers within days of each other, some claiming the black hole model was clearly dominant, others arguing the data was consistent with something no instrument had ever actually seen before. A researcher who spent years studying active galactic nuclei looked at the first detailed spectra and reportedly said the shape made no sense under any framework she had previously used. The V is a fingerprint. Every fingerprint belongs to something. The field just had to figure out what that something was, and the answer each team reached depended heavily on which part of the fingerprint they weighted most. The contest between those answers was about to get very serious. The leading explanation came from a team in Copenhagen, and when it was published in January of 2026, it offered something the field had been craving since the first little red dot was catalogued: a way to explain these objects without requiring anything entirely new to physics. Their model works like this. Picture a young black hole, smaller and lighter than the enormous beasts that anchor modern galaxies, sitting inside a dense cloud of gas in the early universe. The cloud is not diffuse. It is thick, almost opaque, a cocoon of material so concentrated that light struggles to pass through it freely. The black hole at the center is actively feeding, pulling streams of gas from the cocoon inward and accelerating them to extreme velocities. As that gas spirals in, it heats up. Friction, compression, and the intense gravity near the black hole's edge bring the infalling gas to temperatures measured in the tens of thousands of degrees. At those temperatures, the gas glows from within. The heat radiates outward, but the cocoon absorbs and re-emits it multiple times before any photon escapes to the outside. What emerges, after all that reprocessing, is a reddened glow from the dense surrounding material, with flickers of more energetic radiation escaping through gaps in the cloud. The ultraviolet component comes from those leaks, from hot young stars forming in the outer layers of the same system, from ionized gas heated by the radiation pressure and escaping through openings. Put both contributions together and you have something that looks, from a distance, like a V-shaped spectrum. The Copenhagen team's model had one feature that made it especially appealing. The black holes at the center of these objects, under their analysis, were considerably lighter than previous estimates of little red dot black holes. Earlier researchers had assumed, based on emission line widths, that the central black holes were enormously massive. The Copenhagen model suggested that the emission lines were being broadened by the dense gas itself, making the black hole appear much heavier than it actually was. Strip away that geometric effect, and the black hole mass dropped dramatically. That was a relief of sorts. Overmassive black holes in the early universe are already a problem, which you will hear more about shortly. If the little red dots turned out to host black holes several hundred times lighter than previously thought, that particular problem became more manageable. As Professor Derek Watson put it, there was no need to invoke completely new types of events to explain these objects, at least on the black hole mass side. The relief did not last long, because the model, elegant as it was, carried a prediction. Actively feeding black holes produce X-rays. The radiation generated near the event horizon, as matter heats during infall, is energetic enough to penetrate even dense gas cocoons. Any black hole consuming material at the rate required to power a little red dot should be detectable at X-ray wavelengths. When researchers pointed X-ray telescopes at catalogs of confirmed little red dots and looked for that expected glow, the result was quiet. The vast majority of little red dots produced no detectable X-ray signal whatsoever. Some produced nothing at all. For objects supposedly powered by actively consuming black holes, the X-ray silence was a complication the model could not fully explain away. The gas cocoon idea survived, but it was wounded. And in that gap, a second theory arrived from Harvard that made the first one look conservative. The paper from Harvard appeared in February of 2026, and it required readers to stretch their imagination further than most cosmological papers ask. The lead researchers, Devesh Nandal and Avi Loeb, were not proposing a refinement to an existing category of object. They were proposing that the little red dots might be something that has never existed in the modern universe, something that has no analog in any current observation, something that burns with a brightness so extreme it blurs the line between a star and a galaxy. Their idea centers on what physicists call supermassive primordial stars. Forget for a moment everything you know about ordinary stellar masses. Our own star, the star at the center of our solar system, contains enough material to fill more than 1 million Earths. It is, by human standards, incomprehensibly large, but by stellar standards, it sits somewhere in the middle of the mass distribution. Massive stars can reach tens or even a few hundred times our star's mass before the physics of stellar stability breaks down. The Harvard model involves stars roughly 1 million times the mass of our star. To build something like that requires conditions that existed only in the universe's first moments before any heavy elements had been forged. In the cosmic dark ages, gas clouds were composed almost entirely of hydrogen and helium, with no carbon, no oxygen, no nitrogen, none of the molecules that would normally allow a collapsing cloud to cool efficiently and fragment into smaller stellar cores. Without that cooling, the math changes. A metal at a rate that would make its lifetime brief, even by stellar standards. But while it burned, it would outshine entire galaxies of ordinary stars, pouring energy into its surroundings at a rate that staggers calculation. Crucially, the Nandal and Loeb model produced a spectral signature for these hypothetical objects, and the signature matched the V shape. The extreme ultraviolet output from the hot, dense stellar surface explained the blue side of the spectrum. The dense, radiation-processed gas surrounding the star, heated and ionized by that ferocious output, explained the red side. The hydrogen emission lines, seen in the little red dot data, a particularly distinctive spectral feature that the black hole models struggled to reproduce cleanly, appeared naturally in the supermassive star scenario. For the first time, as one of the Harvard researchers put it, we might not be looking at a dead signature of a star, but at something alive. The problem is scale. A single supermassive star, even one shining with the fury of 1 million ordinary stars, requires conditions so rare that explaining hundreds of confirmed little red dot detections through this mechanism alone strains plausibility. These objects would have to form in enormous numbers across the early universe, burning briefly and then collapsing, each one eventually contributing a massive black hole seed to its host environment. The theory is beautiful. The abundance is uncomfortable. Neither model has yet claimed the field, and the conversation about what exactly these objects are shifted in a way that surprised even the researchers closest to the problem. By the middle of 2025, the lead Princeton researcher studying little red dots, Jenny Green, described the situation in a way that was more candid than most public scientific statements ever get. The field, she said, was closing in on an answer. Another researcher involved in the analysis, Anna de Graaf at the Max Planck Institute, went further. The big breakthrough of the preceding months was the realization that almost everything the community had previously thought about these objects needed to be discarded. That is not the language of ordinary scientific progress. That is the language of a conceptual reset. The current state of the debate, as of early 2026, can be summarized in a few hard realities. The gas cocoon black hole model is the dominant working hypothesis. The majority of researchers find it the most physically plausible, but it cannot account for the X-ray silence. An actively feeding black hole of the required mass should be producing X-ray emission at a detectable level. Only 2 little red dots in all the confirmed catalogs show confirmed X-ray emission. The rest are silent, and the silence is not what you would expect if the entire population were powered by consuming black holes in the way the Copenhagen model describes. One possible explanation is that the gas cocoons are even denser than the model assumes, thick enough to absorb the X-rays before they escape. Another is that the black holes are feeding in short bursts rather than continuously catching instruments during their quiet phases. Both explanations are plausible. Neither is confirmed. The supermassive star model handles the X-ray silence naturally. Since a burning star does not produce the hard X-ray radiation, a feeding black hole does. But the abundance problem remains real. Producing hundreds of these objects in the surveyed volume requires a production rate that the early universe would have to sustain with unusual efficiency. The most likely resolution, when it comes, will probably not vindicate either model completely. The little red dot population may contain a mixture of object types, different physical phenomena producing similar spectral shapes in different objects, unified by the extreme conditions of the early universe rather than a single shared origin. Several research teams are already analyzing subpopulations within the catalog, trying to find statistical distinctions that might separate the black hole-powered objects from any hypothetical stellar counterparts. But while that investigation continues, a completely separate alarm was going off in a different part of cosmology, an alarm that had been sounding quietly for over a decade before Webb made it impossible to dismiss. The impossible early galaxies were a crisis in the story of structure formation. The little red dots were a crisis in the story of the first compact objects. What came next was a crisis in something far more foundational, our measurement of the universe's own expansion. And it was the kind of crisis where the more carefully you measured, the worse the problem got. Every cosmologist working today lives with a number that does not match. The universe is expanding. That fact has been established beyond any reasonable doubt for nearly a century. And the rate of that expansion, a quantity called the Hubble constant, has been the central measurement target of modern observational cosmology. Knowing how fast the universe expands tells you its age, its geometry, its ultimate fate. The Hubble constant is not a peripheral detail. It is one of the most consequential numbers in all of physics. The problem is that two completely independent methods of measuring it return two completely different answers. The first method reads the oldest light in the universe. In the moments after the Big Bang, the entire universe was a hot, dense plasma, and sound waves were bouncing through it like ripples in an ocean. When the plasma eventually cooled enough for atoms to form, roughly 380,000 years after the beginning, those sound waves froze in place. Their imprint is preserved in the cosmic microwave background, the faint afterglow of that ancient light that permeates the sky in every direction. Satellite missions mapped that afterglow with extraordinary precision, charting the exact size of those frozen sound wave patterns. From those measurements, combined with the standard cosmological model, you can calculate how fast the universe was expanding at that moment and extrapolate forward to predict its current expansion rate. That prediction lands consistently around 67 to 68 kilometers per second for every 3.25 million light-years of distance. The second method skips the theory entirely and measures expansion directly in the nearby universe. Astronomers identify stars called Cepheid variables, which pulsate with a brightness that varies predictably with their luminosity. By comparing how bright they appear from Earth against how bright they actually are, researchers calculate their precise distances. Those distances anchor the measurement of how fast nearby galaxies are receding. Overlay enough of these calibrations, extend them to supernovae in distant galaxies as an additional distance rung, and you arrive at an independent expansion rate. That measurement returns consistently around 73 kilometers per second for every 3.25 million light-years of distance. 67 versus 73. That gap might sound small. Expressed as a statistical discrepancy, it reaches 5 sigma, meaning if these two measurements were actually describing the same universe with the same physics, the chance of getting a gap this large by random measurement error is roughly 1 in a million. In particle physics, a 5 sigma result is the threshold for declaring a discovery. In cosmology, it means the model connecting the two measurements has a serious problem somewhere. The tension had been growing for over a decade before Webb launched, and then the telescope set out to resolve it. One of the original science goals written into Webb's mission brief was to settle the Hubble tension by making dramatically sharper measurements of Cepheid stars in nearby galaxies. The previous generation of telescopes could see Cepheids at the distances needed, but their resolution in crowded stellar environments was not perfect. A potential explanation for the tension was that older telescopes were accidentally blending the light of Cepheids with neighboring stars in crowded fields, making the Cepheids appear brighter than they really were, which would push the distance measurements, and therefore the expansion rate, slightly upward. Webb's infrared sensitivity and unprecedented spatial resolution were tailor-made to separate individual Cepheids from their surrounding stellar populations. If the local measurement was inflated by contamination, Webb would find it. The measurements came back sharper than any instrument had ever delivered. Individual Cepheids in target galaxies were cleanly resolved, separated from their stellar neighborhoods with a precision the field had never previously achieved. The contamination problem, if it existed, could now be quantified and corrected. The corrected measurements changed the local expansion rate by a small amount. The measurement moved within its error bars, as any result does when you improve precision. It remained comfortably above 70. The gap with the early universe prediction did not close. The Hubble tension held exactly where it was, now confirmed with an accuracy that left essentially no room for the contamination explanation to survive. This result was announced in 2024 and absorbed slowly across the cosmological community. The tension had lasted a decade, and throughout those years, a recurring hope was that improved measurements would eventually reveal the error, allow the two methods to converge, and let the standard model breathe again. Webb was the instrument that was supposed to deliver that convergence. Instead, Webb delivered certainty in the worst possible form, certainty that the problem was real. Adam Rees, who shared the Nobel Prize in Physics for the discovery of cosmic acceleration and who has spent the last decade building the case for the tension through progressively more refined measurements, said the field was wandering in the wilderness. A Nobel laureate, using biblical language to describe the state of his field, is saying something about more than the technical details of a measurement. He was describing a community that had followed a path it trusted for a very long time and arrived at a place where the map no longer matched the terrain. The tension between the two measurements of expansion was now confirmed beyond doubt. What it pointed to, something wrong in the model connecting the early universe to the present one, remained unresolved. And while cosmologists were sitting with that discomfort, a completely separate instrument, aimed at an entirely different target, came back with a result that made the Hubble tension look almost like a preliminary symptom of something far larger. While Webb was staring backward in time at the universe's infancy, a ground-based instrument called the Dark Energy Spectroscopic Instrument was doing something complementary, mapping the modern universe in the most comprehensive survey of cosmic structure ever attempted. Over 5 years of operation, the instrument measured the precise distances and positions of 15 million galaxies spread across enormous volumes of space, building a three-dimensional portrait of how matter has been distributed across cosmic history. The purpose was to track dark energy. Dark energy is the name physicists gave to whatever is causing the universe's expansion to accelerate. Every galaxy in the universe should be slowing down under the mutual gravitational attraction of all the matter within it. Instead, since roughly 5 to 6 billion years ago, the expansion has been speeding up. Something is pushing outward against gravity, and that something appears to account for roughly 68% of the total energy content of the universe. The most mathematically simple description of this substance is a cosmological constant, a fixed energy density that permeates space uniformly and does not change over time. Einstein included it in his original field equations and then famously removed it, only for observations to bring it back decades after his death. The cosmological constant has been the backbone of lambda CDM for decades, and the 15 million galaxy survey was designed to test it precisely by mapping how dark energy has shaped the distribution of galaxies over billions of years. When the analysis was published in 2025, it contained something the cosmological community had not expected. Dark energy appeared to be weakening. The signal was not dramatic by astronomical standards, but it was statistically significant, reaching roughly 4 sigma when the galaxy survey data was combined with information from supernovae and the cosmic microwave background. That means a statistical fluke large enough to explain the result has a probability comparable to finding a winning lottery ticket twice in the same week. The researchers described the result carefully, in the measured language of scientists who know their claim will be scrutinized intensely. But what the numbers said was clear. The repulsive pressure driving cosmic expansion was not holding steady. Across billions of years of cosmic history, it appeared to have been gradually diminishing. A cosmological constant, by definition, does not diminish. If it diminishes, it was never a constant. Something more complex was at work in the fabric of space-time, something that behaved like a fixed energy density in the early universe, but had since evolved, changed, perhaps even begun to fade. John O'Meara, chief scientist at the Keck Observatory, described the result simply. Cosmology, as we know it, may be broken, not tweaked, broken. And the details buried deeper in the analysis held something stranger still. The number returned by the Dark Energy Survey pointed to something stranger than a weakening force. The direction of that weakening, traced back through cosmic history, suggested that dark energy may have crossed a specific theoretical boundary at some point in the universe's past, a line physicists call the phantom divide. To understand why that boundary matters, consider what dark energy is doing in simple terms. The cosmological constant, the standard model version of dark energy, exerts a uniform repulsive pressure, the same everywhere, the same always. Its energy density remains exactly constant as the universe expands. Every cubic meter of space contains exactly the same amount of it, forever. The phantom divide marks a boundary in the space of possible dark energy behaviors. On one side of the boundary sits the cosmological constant and related models, where dark energy dilutes gradually or holds steady as space expands. On the other side sits a regime where dark energy actually grows denser as the universe expands, becoming stronger over time rather than weaker. A behavior that carries implications severe enough to have its own name, the Big Rip. In a universe dominated by a phantom dark energy that grows without bound, the expansion eventually accelerates so catastrophically that it tears apart galaxies, then solar systems, then planets, then atoms themselves. The DESI analysis suggested that dark energy had recently been weakening, crossing through the cosmological constant value and heading in a downward direction. That trajectory, extrapolated backward, pointed toward a past in which dark energy was stronger than the cosmological constant, possibly stronger than current models accommodate, possibly crossing the phantom divide in the early universe. UC Berkeley physicist Eric Linder, one of the researchers involved in interpreting the results, called the finding beautifully bizarre. That description, half wonder and half alarm, captures the specific sensation of watching the data suggests something that the standard framework has no clean language for. Here is what the phantom divide actually represents in practice. The standard cosmological model is built on an equation of state for dark energy that sits at a specific value and stays there. If dark energy has crossed the phantom divide, no single smooth, well-behaved field in standard physics can describe it. The mathematics requires either multiple interacting fields, or modifications to gravity itself, or something about the nature of space-time that current theoretical tools are not fully equipped to handle. The phantom divide marks the line between what standard physics can comfortably explain and what it currently cannot. The DESI result was framed carefully as a strong hint requiring more data rather than a confirmed detection. At the level of certainty established so far, alternative explanations remain possible. The full 5-year data release from the instrument, carrying considerably more statistical weight, would sharpen the picture substantially. But even the hint carried weight, because when cosmologists began looking at what the DESI result implied in combination with the Hubble tension, they found something that stopped every proposed solution in its tracks. 2 crises, each pointing towards something broken in the standard model. Each with its own proposed fixes, each with its own community of researchers exploring solutions. The natural expectation was that a good solution to one would at least not make the other worse, and ideally might address both. The expectation was wrong. When theorists began testing cosmological models that allowed dark energy to evolve over time, the kind of model the DESI data was pointing toward, they found that incorporating that evolution did something unexpected to the Hubble tension. Allowing dark energy to change removed some of the strain in fitting the galaxy distribution data. But the same modification that eased that fit altered the early universe expansion history in a way that pushed the 2 measurements of the Hubble constant further apart, not closer. Fixing the dark energy problem widened the Hubble tension. Conversely, attempts to resolve the Hubble tension through modifications to the early universe, adding brief energy injections before the cosmic microwave background was released, tinkering with the acoustic scale in ways that would bring the 2 expansion measurements into agreement, tended to produce galaxy distribution predictions that clashed with what the DESI survey actually measured in the nearby universe. Fixing the Hubble tension strained the dark energy picture. The 2 problems are not independent, they are coupled, linked through the same underlying cosmological equations, and any change to one part of those equations propagates to the other. The field had been treating them as separate puzzles to be solved on separate timelines with separate tools. The emerging evidence suggested they were more like 2 symptoms of a single deeper illness, something wrong at the level of the model's foundational assumptions, threading through both the expansion rate and the behavior of dark energy simultaneously. This is the double bind, 2 confirmed, high-significance anomalies, solutions to one that actively worsen the other. A theoretical landscape in which no proposed single patch covers both holes at once. Michael Boylan-Colchin, one of the researchers most closely tracking the galaxy count crisis, put it plainly in an interview. The number of anomalies that have piled up is simply too large to be coincidental. and they are too correlated to be independent failures of independent systems. The Standard Model is not wrong in one place. It appears to be strained across multiple, interconnected areas simultaneously. The field now faced a choice that had no comfortable option. Either each anomaly would eventually find its own small fix and Lambda CDM would survive, battered but intact. Or the anomalies were symptoms of something structural, something that required not patching the model but rebuilding it from a deeper level. Neither path was easy. And while cosmologists wrestled with those two possibilities, Webb had delivered yet another category of impossible object, one that appeared not in the galaxy distribution statistics but in the measurement of mass itself, inside the earliest compact objects the universe ever produced. When a black hole feeds, physics imposes a ceiling. As matter falls toward a black hole, it does not plunge directly inward. It spirals, forming a disk of rapidly rotating material around the black hole's edge. Friction in that disk heats the gas to millions of degrees, and the hot gas radiates furiously, pouring energy outward in all directions. Some of that outward radiation pushes back against the infalling material. When the radiation pressure becomes strong enough, it counterbalances gravity and slows the rate at which new matter can fall in. This ceiling is called the Eddington limit, and it describes the maximum rate at which a black hole can accumulate mass before its own luminosity begins to choke off its fuel supply. The limit scales with mass. A more massive black hole can eat faster in absolute terms, but even the largest black holes are constrained by this physical ceiling on their growth rate. Now, apply that constraint to a timeline. Take the smallest reasonable starting point, the most massive black hole seed that standard physics can produce through stellar collapse. Start feeding it at the maximum Eddington rate from the first moment the universe allows it. From the earliest possible moment, stars could have formed and died and left behind black hole remnants. Follow the growth curve forward in time at maximum theoretical speed. When JWST found a black hole containing mass equivalent to roughly 1.5 million times our star, sitting in a galaxy at 460 million years after the Big Bang, the number sat close enough to the theoretical growth curve that it raised questions without definitively breaking the model. Uncomfortable, but arguable. Then came the objects at 700 to 800 million years after the Big Bang, carrying hundreds of millions to several billion times the mass of our star. Then came hints of even heavier objects at even earlier times. At those masses, at those moments, the Eddington limited growth curve does not come close. A black hole starting from any plausible stellar remnant and growing at the absolute maximum rate from the very beginning of star formation has no path to that mass in that time. The clock was broken, one of the most fundamental and rigorously tested constraints in astrophysics. A limit derived from basic principles of radiative physics that had never been observed to fail in any system in the modern universe, was giving numbers that Webb's objects simply could not satisfy. The Standard Model of black hole growth, one that had been validated in every accessible context, was producing timelines that required the early universe to do something the physics said was impossible. Some researchers sat with the data and tried to identify where the constraint might have room to flex. Others began building models that required starting conditions the Standard Model does not provide. The conversation about what these overmassive early black holes actually meant for the underlying physics was only beginning, but it already carried one clear conclusion. The early universe was producing black holes faster than the universe had any business producing them. 3 possible explanations for overmassive early black holes circulate through the current literature, and each one requires either stretching or abandoning something in the established framework. The first is called the heavy seed scenario. Standard black hole formation produces seeds from the collapse of massive stars, remnants that weigh roughly tens to perhaps a few hundred times the mass of our star at the upper end. In the heavy seed scenario, the early universe bypassed that process entirely. Massive clouds of primordial gas, under certain temperature and density conditions that may have existed only in the very early cosmos, collapse directly into black holes without ever forming stars at all. Direct collapse black holes, as they are called. could begin their lives with masses already tens of thousands of times heavier than the most massive stellar remnant. Starting that much heavier, an Eddington limited growth curve can reach billion solar mass territory faster. The math improves. The problem is that the conditions required for direct collapse are narrow and specific. The gas cloud must be prevented from fragmenting into stars, which typically requires an intense radiation field destroying the molecular hydrogen that normally initiates star formation. Such conditions, but a thick, puffed-up torus that traps radiation differently, or brief episodes of extremely high inflow rate that the radiation field cannot catch up with quickly enough to choke. Some theoretical models suggest super Eddington feeding could multiply the effective growth rate by factors of several to perhaps a few tens, which would dramatically shorten the time needed to reach extreme masses. The third explanation is the most radical. Primordial black holes, objects formed not from stellar collapse but from density fluctuations in the very first fraction of a second after the Big Bang, before any star ever burned, could have entered the universe already massive. If such objects exist, and formed in significant numbers during that primordial moment, they could have been the seeds from which the overmassive early black holes grew with less time pressure. The primordial black hole hypothesis has existed for decades as a theoretical possibility, never confirmed, never definitively ruled out, living in the uncertain territory between cosmological speculation and legitimate scientific candidate. The troubling reality is that none of these three explanations covers every confirmed case. Some of the overmassive early black holes that JWST found can be accommodated by direct collapse, some by super Eddington feeding, some might point toward primordial seeds. A full accounting of the entire observed population requires a combination of mechanisms, each of them operating outside what the standard model treats as normal. In a universe whose first moments appear more productive and more violent than any simulation had captured, each proposed solution points back toward the same uncomfortable conclusion. The early universe was building things faster, heavier, and more efficiently than the physics the field inherited from the 20th century can explain. The impossible galaxies were doing it. The overmassive black holes were doing it. And the questions those objects raised were about to converge with the Hubble tension and the dark energy problem in a way that forced the entire cosmological community to ask something it had been quietly avoiding. The young universe was swimming in gas. Every model of early cosmic structure agreed on this basic fact. The first few billion years were rich with raw fuel, hydrogen and helium flooding the spaces between nascent galaxies, pouring inward along filaments of dark matter to feed new generations of stars. The expectation was reasonable. If anything, the early cosmos had more raw material available than it does today. More of it within reach of any galaxy trying to grow. Webb found galaxies that had already burned through all of it, catastrophically and impossibly early. Across multiple survey fields, the telescope confirmed what astronomers call quenched galaxies. Massive systems containing billions of stars, but producing no new ones. Their star formation histories complete, their gas supplies exhausted or expelled. In the modern universe, dead galaxies exist in abundance, mostly large ellipticals that used up their fuel several billion years ago and have been coasting ever since. Quenching is normal. It is just supposed to take time. In the deep Webb data, quenched galaxies were appearing at redshifts, placing them in the universe's first billion years. Some had stellar masses comparable to a large modern galaxy, but had completely stopped forming stars before the universe reached that single billion-year mark. Star formation timescales in these objects ran as short as 100 to 500 million years. By the time they were observed, they had already lived their entire active lives in what amounted to a cosmic blink. The models had a serious problem with this. Galaxy quenching in the standard picture takes time, because the mechanisms that shut down star formation require a buildup of effects that do not happen quickly. Supernova feedback, the cumulative result of thousands of stellar explosions, pushing gas outward and heating the surrounding medium, is one candidate. But feedback from supernovae alone generally needs billions of years to fully suppress star formation in a large galaxy. The quenched objects Webb found had accomplished this in a fraction of that time. Something more powerful was shutting these galaxies down, something operating far earlier than any simulation had reliably reproduced. The natural suspect was sitting at the center of each of these galaxies, invisible but enormously energetic, capable of releasing more power in a single year than a typical star emits across its entire lifetime. A supermassive black hole, feeding and pushing. But the mechanism turned out to be stranger than a simple explosion. When one particularly well-studied case from a Cambridge team was analyzed in detail, the picture that emerged was more insidious than a single catastrophic event. The galaxy in question had not been blasted apart. It had been quietly starved. Its central black hole was producing no dramatic jets of plasma. There were no massive outbursts of radiation boiling away the molecular clouds. Instead, the black hole was doing something slower and, in its own way, more effective, gradually, steadily, and continuously removing the gas that would otherwise have collapsed into stars, disrupting the cooling flows that would normally allow that gas to condense and form new stellar nurseries, keeping the fuel permanently turbulent and permanently warm. The galaxy died by attrition. Its entire active life, from the first star forming to the last one switching on, fit inside a sliver of cosmic history that the models had expected to be full of growth. The new question was immediate. If a quiet, steady black hole could do this to a galaxy in the universe's first billion years, what did the surviving galaxies look like? What shapes did the ones that escaped this fate manage to build in the brief, violent window of early cosmic time when everything was being assembled at speed? The Cambridge team published their analysis in early 2026, and the details were precise enough to feel almost forensic. A massive galaxy at a redshift placing it in the universe's first billion years, fully assembled stellar population, no ongoing star formation, the gas that might have fueled new stellar nurseries was present in the surrounding environment, but something had kept it from collapsing. The culprit was the central black hole, and its method was quiet enough to be almost invisible in the data, until the team built a complete picture of the galaxy's thermal history. In the popular imagination, black holes in the centers of galaxies destroy their hosts through violence. Jets of plasma fired at near light speed, titanic outbursts of radiation, energetic enough to boil away entire molecular clouds. These eruptions are real, and they can clear enormous amounts of gas in short order. The galaxy in the Cambridge analysis showed something subtler and ultimately more efficient. The black hole was cycling, producing a steady stream of lower energy disturbances, injecting just enough thermal energy into the surrounding gas to keep it from cooling below the threshold where gravity could collapse it into new stars. Each injection was small, none of them constituted a dramatic event. Their cumulative effect, repeated across hundreds of millions of years, produced a galaxy-wide suppression of star formation that no single explosion could have achieved as consistently. Researchers have a name for this mode of feedback: maintenance mode. The black hole maintains the galaxy's temperature, its gas held in a state of permanent restlessness, never cold enough to form stars. The fuel supply is present. The black hole is simply ensuring the fuel never becomes usable. In the modern universe, this kind of regulation is observed in large elliptical galaxies at the centers of galaxy clusters, where the central black hole cycles through periods of activity and quiet, keeping the surrounding intracluster gas from cooling and raining down as star-forming material. The behavior is documented. The physics is understood reasonably well at those late cosmic epochs. What Webb revealed was that the same process was already operating in the universe's first billion years. a mechanism thought to govern the long, slow aging of mature galaxy clusters, was already shutting down young galaxies in the earliest chapters of cosmic history, working efficiently enough to fully quench a massive system before most of the universe's galaxies had even finished assembling their first stellar populations. The implications for galaxy evolution timelines were immediate. If black holes could regulate and terminate star formation this early and this efficiently, then the history of galaxy growth was far more controlled, far more self-limiting than any previous model had assumed. Galaxies did not simply keep growing as long as gas was available. They carried within them a self-limiting mechanism, timed by the growth rate of their own central black holes, capable of switching off the engine long before the universe ran out of raw material. The death of a galaxy by 1,000 quiet cuts, operating in cosmic infancy. And while these dead galaxies were raising questions about timing and regulation, the surviving galaxies, the ones that had not been quenched, were raising a completely different kind of question. Their shapes were strange, and not in a way that reflected a single unusual formation event. The geometry of the earliest surviving galaxies pointed towards something deeper, something about the invisible substance that makes up most of the universe's mass. The shapes of the first galaxies were trying to tell the field something about dark matter. And the message was not what anyone expected. Galaxies come in shapes, and the shapes carry history. Every amateur astronomer knows the basic categories: the sweeping arms of a spiral, the smooth glow of an elliptical, the chaotic form of an irregular. These forms are not random. They emerge from physics, from the angular momentum of a collapsing gas cloud, from the history of mergers, from the age and mass of the stellar population inside. Shape is biography. A galaxy's appearance encodes what happened to it across billions of years. The earliest galaxies Webb found were shaped in a way that the standard model had not predicted. Stretched, elongated, rod-like, almost cigar-shaped, existing less than 1 billion years after the Big Bang, before any of the familiar rounded or spiraling forms had time to develop. These objects had a geometry that looked nothing like the irregular clumps the model expected, and nothing like the more organized shapes of later cosmic epochs, pointed at both ends and extended along a single axis, like something squeezed in one dimension while the universe was still assembling. A team publishing in Nature Astronomy in December of 2025 ran simulations trying to reproduce this elongation using the standard ingredient for dark matter: cold, slow-moving, massive particles that clump on small scales and build structure hierarchically. The component lambda CDM calls cold dark matter. The simulations consistently failed. Cold dark matter produces halos that are somewhat elongated, but not to the degree observed in the earliest Webb galaxies. The specific geometry of what the telescope was finding did not appear in the output. Then the team tried a different ingredient entirely. Wave dark matter, also called fuzzy dark matter or ultralight dark matter, consists of particles so extraordinarily light that they behave quantum mechanically on scales comparable to entire galaxies. Rather than clumping into discrete particle distributions, wave dark matter forms interference patterns, spatial structures shaped by the quantum nature of the particles themselves. The halos built from wave dark matter have a different internal geometry. Specifically, they produce elongated, rod-like shapes more naturally, particularly in the early universe when halos are young and quantum effects are most prominent. When the team ran simulations with wave dark matter as the key ingredient, elongated shapes appeared with a frequency that matched what Webb was observing. Cold dark matter produced the wrong geometry. Wave dark matter came considerably closer to the right one. The researchers stated clearly that this was a preliminary result from a single study. One paper does not a paradigm shift make, but the result pointed toward a possibility that the particle physics community had long found uncomfortable. The dark matter particle that laboratory experiments have spent decades searching for might be entirely the wrong mass. Dark matter comprises roughly 27% of all energy in the universe. Its nature is completely unknown. Decades of underground detectors, particle accelerators, and astrophysical searches have failed to find a direct signal from any specific dark matter candidate. And now, the shapes of galaxies in the universe's first billion years were suggesting that the invisible scaffolding from which all cosmic structure was built might be composed of something far lighter, far stranger, and far more quantum mechanical than anyone had designed their experiments to find. The universe was piling up its revelations. Dead galaxies, starved galaxies, galaxies with shapes that challenged the composition of dark matter itself. None of these findings existed in isolation. Each one connected to the others through a web of implications that was growing impossible to map with the tools the field had relied on for 4 decades. The time had come to stop examining anomalies one at a time and place all of them on a single table. Step back from the individual discoveries. For months and then years, each anomaly arrived on its own schedule, announced by its own team, absorbed gradually into a field already processing the previous surprise. Early galaxies, too bright. Little red dots with no category. A Hubble tension confirmed at 5 sigma. Dark energy apparently weakening. Overmassive black holes. Dead galaxies too early. Galaxy shapes pointing toward a different form of dark matter. Placed side by side, the list reads differently than it does one item at a time. The standard cosmological model, lambda CDM, makes specific, testable predictions for all of these things. It predicts the brightness distribution of early galaxies. It predicts the Hubble constant. It predicts the behavior of dark energy. It predicts how fast black holes can grow. It predicts how long galaxies take to exhaust their star-forming fuel. It predicts the shapes of early halos. On every one of those predictions, the data from Webb and from DESI and from the Hubble tension measurements disagrees. That pattern does not resemble a model with a small error in one of its parameters. A single miscalibrated number typically produces a small, systematic offset in one observable while leaving others intact. The pattern visible in the JWST error looks different. Multiple independent observables, each measured by different instruments using different techniques, all pulling in the same direction. Each one says the early universe built structure faster, deeper, and more efficiently than the standard model predicted. Proposed solutions exist for each anomaly individually. Bursty star formation for the early galaxy brightness, modified expansion history for the Hubble tension, evolving dark energy for the DESI signal, exotic black hole, seeding for the overmassive early compact objects, alternative dark matter for the elongated shapes. The proposed solution list is as long as the anomaly list. The problem emerges when researchers try to apply these solutions simultaneously. Every time a theorist adjusts the model to fit one anomaly, the adjusted model produces worse predictions for at least one other. Fixing the Hubble tension through early dark energy changes the pattern of galaxy clustering in a way that conflicts with the DESI survey, allowing dark energy to evolve as the DESI data prefers, widens the Hubble tension rather than closing it, boosting star formation efficiency to explain the early galaxy brightness helps but does not fully account for the factor of more than 100 in number density excess. The anomalies are coupled. They are woven together through the same equations, and pulling on one thread tightens others. Pedro Ferreira, a cosmologist at Oxford, described the state of the field with the kind of honesty that takes time to reach in a scientific community. There is simply too much going on to say anything truly definitive. That admission from a physicist who has spent his career building and testing cosmological models is its own kind of finding. The anomaly count is too high. The correlations between them are too tight. Proposed patches cannot resolve matters cleanly. The field was approaching a choice with no comfortable version. Either every anomaly would find its own small, independent fix, and the model would survive battered but standing, or the pattern of correlated anomalies pointed towards something structural, something wrong not in one parameter but in the foundations. Before that reckoning could arrive, the simplest class of solution deserved a proper hearing, the kind that requires no new physics, no new fields, no new particles, just a re-evaluation of what the first galaxies were actually doing when they were young. Before abandoning any model, responsible science asks whether a simpler explanation can do the work. In the case of the early galaxy crisis, one simpler explanation arrived from observations of the most primitive galaxies close enough to study in detail. Dwarf galaxies, small and irregular, contain some of the oldest stellar populations accessible within a reasonable distance. Studying them closely revealed a behavior pattern that more massive galaxies in rich environments tend to suppress. Star formation does not proceed at a steady, sustained rate. Instead, it happens in violent, concentrated bursts, separated by longer periods of quiet. A galaxy in burst phase can produce new stars at a rate 10 to 50 times higher than its average over millions of years. During that burst, its luminosity surges dramatically. A galaxy with a modest total stellar mass might, at any given snapshot in time, appear far brighter than that mass would suggest, because all its star formation is compressed into a brief, furious episode, rather than spread evenly across cosmic time. This is called bursty star formation, and it offered a possible escape route from the galaxy brightness crisis without invoking anything exotic. If the earliest galaxies formed stars in violent bursts rather than at steady rates, Webb might simply be catching many of them during peak activity. Their intrinsic masses might be more moderate, consistent with what the models produce. Their apparent brightness would be misleadingly high, because the telescope is finding them at their most luminous moments. Averaged over longer timescales, the population might be less catastrophically in conflict with predictions. The explanation had genuine appeal. Bursty star formation is observationally supported in nearby dwarf galaxies. The conditions in the early universe, where gas was more turbulent, gravitational instabilities were stronger, and the absence of heavy elements changed the cooling physics, would plausibly amplify this behavior. A case could be made that the primeval cosmos was bursty by nature, and that earlier simulations had been using star formation recipes calibrated on the modern universe, where conditions are calmer. Partial credit, the field decided, was warranted. The bursty star formation explanation almost certainly captures something real. Some of the early galaxies Webb found are probably in burst phase, appearing more luminous than their underlying mass justifies. Incorporating more realistic bursty behavior into simulations does bring predicted brightness distributions closer to observed ones, but partial credit means partial failure. Finding a factor of more than 100 excess in the count of bright early galaxies requires more than a boost in apparent luminosity. It also requires more galaxies forming earlier and more efficiently than the standard model produces. Burstiness makes individual galaxies look brighter. It does not create more of them. The sheer number of massive, luminous early systems, confirmed across all survey fields, remains above what any bursty star formation model, calibrated on nearby observations, can accommodate cleanly. The simplest fix covered part of the territory. The rest required something that reached further, something that changed not the behavior of the galaxies themselves, but the conditions in which they formed, reaching back to the universe's earliest moments before the first star ever ignited. The simplest cosmological fix targets something that happened before galaxies, before stars, and before atoms existed in their current form. In the standard model, the universe's first 380,000 years were a period of expansion from the initial hot, dense state. The cosmic microwave background carries a record of what the universe looked like at that precise moment. The imprints in that ancient light tell cosmologists about the density fluctuations, the primordial wrinkles that would eventually grow into all the structure visible today. Early dark energy is a proposed modification to what happened in those first hundreds of thousands of years. before the background light was released, inject a brief, powerful burst of additional dark energy into the very early universe, concentrated before the background light was emitted, and two things happen. The expansion rate during that window increases slightly, and the density fluctuations, the seeds of all future structure, get a boost in amplitude, meaning they start out slightly larger and more pronounced than the standard model produces. Larger initial fluctuations lead to earlier structure formation. Dark matter halos collapse sooner, gas falls in sooner, stars ignite sooner, galaxies assemble sooner and grow more massive in any given slice of time than the unmodified model allows. Simulations incorporating early dark energy showed that the approach could bring the predicted distribution of massive early galaxies into meaningfully better agreement with Webb's observations, without requiring exotic physics in the galaxies themselves. The adjustment operates upstream of everything, in the universe's first moments, and propagates forward into results that match what the telescope found. The appeal is real. The controversy is equally real. Early dark energy requires an entirely new field, a new form of energy density that behaved powerfully in the universe's first chapter and then faded away, leaving no other detectable signature in the present. No laboratory experiment has independently detected it. No direct observational constraint requires it on its own. Its current support comes from a single argument. Adding it to simulations makes the galaxy distribution look more like what Webb sees. That is a legitimate form of scientific argument. Models are tested by whether they reproduce observations, and a model that does so better than the previous one deserves serious consideration. But introducing an entirely new energy field on the basis of one class of observation, without independent theoretical motivation, makes many cosmologists deeply uncomfortable. The discomfort is not irrational. The history of cosmology contains extra fields added to explain anomalies that later turned out to have simpler resolutions. Caution is appropriate, and there are concrete problems. There were solutions that asked for something even more fundamental to change, the kind of solutions that sat at the very edge of what a physicist considers thinkable. The proposals at the far edge of the solution space are the ones that cosmologists discuss last and most carefully, because accepting any of them would require revising parts of physics tested to extraordinary precision and found reliable in every accessible context. Modified gravity is the most disruptive candidate. General relativity, Einstein's description of how mass and energy curve spacetime, has passed every experimental test thrown at it for over a century. Binary pulsars, gravitational wave detections, the bending of light around massive objects, the dynamics of our own solar system. No single observation has ever definitively violated it. For this reason, modifying gravity is not a popular move. The bar for doing so is extremely high. But that bar may be relevant only in the regimes where gravity has actually been tested. General relativity has been verified at human scales, at solar system scales, and in the dynamics of binary compact objects. On the scale of galaxy clusters and the cosmic web itself, its predictions remain largely inferred through the standard model rather than tested directly from first principles. A modification that operates only on cosmological scales, leaving smaller scale physics untouched, is theoretically conceivable and not yet directly constrained by any existing test. Several groups have built modified gravity frameworks that reproduce aspects of the JWST observations more naturally than lambda CDM does. These models typically change the effective gravitational constant on the largest scales, allowing structure to grow faster at early times without requiring additional dark matter or dark energy components. Galaxy distributions and number densities can be brought into better alignment with observations without adding new energy fields. The scientific community's response to these proposals is polite and cautious, the specific kind of politeness that signals deep skepticism. A modification to gravity is not a small adjustment. It rewrites the foundation on which all of modern astrophysics stands. Primordial black holes occupy a different corner of the solution space. If the very first moments of the universe produced black holes directly from density fluctuations, before any star formed, these objects could have served as massive structure seeds, concentrating dark matter halos around them and dramatically accelerating the formation of the first galaxies. They could also explain the overmassive early black holes Webb found, since those objects would not need to have grown from stellar remnants at all. They would have arrived already large. Primordial black holes have never been confirmed. Their existence is constrained by multiple indirect measurements, and most of the mass ranges where they could be abundant have been observationally restricted. A specific window in the mass distribution remains open, and a population in that range could plausibly do the structural work the early universe anomalies seem to require. Wave dark matter offers a smoother modification, replacing cold dark matter with lighter, faster-moving particles changes small-scale halo structure without dramatically altering large-scale behavior. It addresses both the galaxy number density and the elongated shapes observed by Webb, attacking two independent anomalies with a single change to the dark matter description. None of these radical options has been ruled out. None has been confirmed. They represent the frontier of what science considers thinkable, the proposals that get seriously entertained when conventional solutions fall short. At this particular moment, with conventional solutions demonstrating their limits one after another, the frontier is more crowded than it has been in decades. Through all of this, the standard model was still standing. That itself was something that needed explaining. Lambda CDM has absorbed blow after blow since Webb opened its eye. Impossible early galaxies confirmed at 6 sigma confidence. A Hubble tension verified beyond any instrumental explanation. Dark energy apparently weakening in ways the cosmological constant cannot accommodate. Overmassive black holes violating every growth timeline. Dead galaxies too early. Shapes that challenge the dark matter framework. A list of anomalies that reads, from a distance, like an indictment of everything the standard model claims about the cosmos. And yet, as of early 2026, the model had not collapsed. Lambda CDM remained the working description every cosmologist used, the tool every simulation was built on, the baseline against which every new result was measured. This is, on reflection, the strangest fact in modern cosmology. A model that fails this many predictions in one concentrated domain of observation would typically be abandoned, or at least formally flagged as broken, in any other branch of science. The history of physics contains clear examples. The ultraviolet catastrophe at the turn of the 20th century, where classical mechanics failed to predict radiation from hot objects and was replaced by quantum mechanics. The precession of Mercury's orbit, which Newtonian gravity could not account for and which required general relativity to explain. When models fail clearly and repeatedly, they get replaced. Lambda CDM has survived because no successor exists to replace it. Without a better model, even a strained model is more useful than no model at all. The standard framework is wrong about something in the early universe, but across most of cosmic history, outside the specific domain of the earliest galaxies and the specific measurements of expansion and dark energy that Webb and DESI have targeted, it works. Galaxy clustering in the modern universe, the distribution of the cosmic microwave background across the sky, Big Bang nucleosynthesis, the production of light elements in the first minutes. All of these remain in good agreement. The failures are concentrated and specific. The successes are broad and precise. Adam Rees, whose Nobel Prize-winning work on cosmic acceleration helped build the very framework now under strain, described the community's position bluntly. People are uncomfortable wandering in the wilderness. That statement goes beyond a technical assessment of a measurement discrepancy. It describes a community that knows something is wrong, that its current tools are insufficient to identify exactly what, and that has no clear path yet toward what will replace the model. The sociology of a scientific crisis matters as much as its physics. Researchers rarely abandon the model they have spent careers building on the basis of anomalies, however numerous. When no successor is ready, The practical cost of abandonment is too high, so the field absorbs the anomalies, publishes papers on their individual proposed resolutions, and continues using the model while quietly hoping the next instrument, the next data release, the next survey, will clarify which failure is the fundamental one. What Webb had delivered, before anyone fully absorbed it, was one more anomaly that nobody had predicted. The problem was a direction. The universe, the data was suggesting, might have a preferred orientation, and if that were confirmed, the foundations would crack at a level that no patch, however creative, could cover. Cosmology rests on two foundational assumptions about the large-scale universe. The first is homogeneity. Matter is distributed uniformly when you average over large enough volumes. The second is isotropy. The universe looks the same in every direction, with no special orientation, no preferred axis, no built-in asymmetry embedded in the fabric of space itself. Both assumptions are central to how the standard model is written. The equations that describe an isotropic, homogeneous universe are simpler and more tractable than the equations required for a universe with a preferred direction. The assumption of isotropy is not a convenience, it is load-bearing. Webb's deep surveys of the earliest galaxies, analyzed for their rotational properties, produced a pattern that made several teams look very carefully at their analysis before publishing. Roughly 2/3 of the earliest confirmed galaxies appear to rotate clockwise when viewed from a consistent reference direction. The number is striking because it should, in a universe without a preferred axis, hover close to 50%. By chance alone, roughly half of all galaxies should rotate in each direction. An excess of 2/3 sustained across the full survey, covering large patches of sky, implies either a statistical fluctuation of meaningful magnitude or something embedded in the universe's initial conditions that introduced a preferred rotation direction in the earliest structures. The researchers involved were careful, as scientists always are when results carry implications this large. The detection sits at a level of confidence that demands follow-up rather than celebration. Independent surveys with different instruments and different analysis methods are needed to confirm or refute it. The result has not been reproduced across enough independent datasets to reach a definitive claim, but the nature of what is being suggested demands attention regardless of whether the specific numbers hold. Individual galaxies acquire their rotation through local gravitational interactions, through the transfer of angular momentum during mergers and gas infall. Standard galaxy formation contains no mechanism that would cause a majority of galaxies across vast cosmic distances to prefer the same direction. The scale of the correlation, spanning more territory than any local physical process could connect, points towards something imposed from the very beginning. The Big Bang, in the standard model, produced a universe without a preferred direction. The initial conditions were assumed to be isotropic by construction. If the galaxies disagree, the initial conditions may have been different from what the model assumed. A universe born with some angular momentum of its own. A universe with some embedded asymmetry at the deepest level, propagating forward into the rotation statistics of the first galaxies. General relativity permits rotating universes. They are called Gödel universes, and they are deeply strange. A rotating universe can contain closed, time-like curves, paths through space-time that loop back on themselves, which raises its own profound questions. The standard model excludes this possibility by assumption. Questioning that assumption may be premature. It may also be exactly the right question for this specific moment in history. The anomaly list had grown long enough that a completely different kind of question became unavoidable. What universe would actually generate all of these things together? Lay out all the pieces. Massive, luminous galaxies confirmed at 280 to 290 million years after the Big Bang. A number density of bright early objects more than 100 times higher than the standard model predicts. Little red dots with a spectral shape that fits no existing category. Supermassive black holes whose mass at 400 to 800 million years after the Big Bang exceeds what any standard growth timeline can produce. dead galaxies quenched before the universe reached its first billion years. Galaxy shapes pointing toward a form of dark matter the standard model does not include. Two independent measurements of the universe's expansion rate, differing by 5 sigma. Dark energy apparently weakening over time, possibly crossing a theoretical boundary the cosmological constant cannot accommodate. And early galaxies whose rotation statistics hint at a preferred direction embedded in the cosmos from its first moments. What kind of universe actually produces all of that? The standard model produces a universe that fails on every one of those points. The revised universe the data is pointing toward would need to be different in several coordinated ways simultaneously. Its expansion history in the first few 100,000 years would need to depart from the lambda CDM description, either through early dark energy, a modified initial expansion rate, or something else that left the cosmic microwave background largely intact while accelerating the growth of density fluctuations. The first structures would need to have assembled faster, driven by more favorable early conditions, and possibly a different dark matter particle, one that clumps more efficiently at earlier times than cold dark matter does. The dark matter itself might behave quantum mechanically on galactic scales, producing the elongated early galaxy shapes that cold dark matter simulations miss. The dark energy driving the current acceleration might be an evolving field rather than a constant, changing its strength over billions of years in ways that explain both the deci-galaxy distribution measurements and the directional trend in the expansion rate. The initial conditions of the Big Bang might not have been perfectly isotropic. Some small asymmetry, possibly in the angular momentum of the primordial plasma, might have propagated forward into the rotation statistics now visible in the earliest galaxies. Taken together, this is not a list of small adjustments to lambda CDM. It is a description of a genuinely different cosmological model, one that shares the successful predictions of the standard framework in the well-tested domains, while departing from it at the frontier where the data has been pointing. No such model currently exists in complete, mathematically rigorous form. The pieces have been proposed separately by separate groups, in separate papers, assembling them into a coherent, self-consistent framework, one that reproduces all the anomalies simultaneously without violating the things lambda CDM gets right, is the central unsolved problem in modern cosmology. It is also, without question, the most exciting problem in modern cosmology. When a framework breaks in multiple correlated places, what typically follows is not a quiet series of patches. It is a revolution, the kind that gives the field a new language for describing reality, a new set of tools for building predictions, and a new generation of experiments designed to test ideas the previous framework did not even ask. The telescope that provoked all of this did not set out to start a revolution. It set out to confirm the last chapter of a story the field thought it had already written. What it found instead was that the story was just beginning. Go back to the beginning. In July of 2022, when the first deep field images came down from a telescope 1 million miles from Earth and moved people to tears, the feeling in the scientific community was triumphant. $1 billion machine, decades in the making, staring into a patch of sky no larger than a grain of sand held at arm's length, had captured thousands of galaxies, ancient light that had traveled farther than any previous instrument could reach. The telescope was supposed to confirm things, finish the picture, built to find the universe's first light and show the world that the map cosmologists had drawn across 4 decades of painstaking observation was correct in its final, hard-to-reach corners. Funding agencies, scientists, and the public had accepted the cost, the delays, the engineering crises, and the 20-year wait on the understanding that the machine would answer the deepest questions with the authority only direct observation can provide. What it actually delivered was a crisis that no one had written into the Riki mission proposal. Every chapter of this story was a record-breaking, the most distant confirmed galaxy, dethroned twice within a year, the most detailed early universe spectroscopy ever achieved, revealing oxygen in places, and at times that oxygen had no right to exist. The most precise measurements of the Cepheid distance ladder, confirming the Hubble tension rather than resolving it. The first confirmed detection of a completely new class of astrophysical object, the little red dots, never predicted and never seen before. The first clear documentation of galaxies dying in the universe's infancy, killed by the quiet persistence of their own central black holes. Running under all of it, confirmed by 15 million galaxies mapped in the nearby universe. An erosion of the cosmological constant that the Standard Model had built its description of spacetime around. The machine did exactly what it was supposed to do. It looked, it measured, it recorded what was actually there, without regard for whether what was there matched the predictions of the people who built it. That is the only version of science that works. The version that trusts the data more than the theory when the two disagree. What the data said, repeated across hundreds of observation programs, independent teams, multiple instruments, and years of accumulated results, was that the universe in its infancy was not the quiet, gradually assembling place the Standard Model described. It was faster. It was more productive. It built structures of shocking complexity in windows of time the model had reserved for tentative beginnings. And it did all of this inside a cosmos that may not be the perfectly symmetric, directionless expanse the equations assumed. The question the telescope was really asking, from the moment its mirror locked into place, was not the question on the mission proposal. The proposal asked, can we find the universe's first light? The telescope answered that question easily. The deeper question, the one that every strange result has been pointing toward, is older than any instrument and sharper than any observation. How much of what we believe about the universe is true, and how much is a story we told ourselves because the evidence was not yet good enough to contradict it? The answer, Webb has been returning, discovery by discovery, image by image, spectrum by spectrum, is unsettling and exhilarating in equal measure. We were looking at a grain of sand held at arm's length and thinking we understood the beach. The telescope moved closer, and the beach turned out to be larger, stranger, and far more alive than the map had room for. The universe is more interesting than we were afraid it would be. The questions have only just started arriving.